All right, folks, here's the big payoff of studying functional groups. Now that we have that vocabulary at our disposal, it's easier to start discussing which functional groups, and therefore which molecules, can do the reactions we've been discussing to this point. We'll start with the addition reactions, and remember that right away we're restricted to functional groups that contain double bonds. But not all double bonds are created equal. Let's take a look at the worksheet. So in our workshop, we saw that there was just one type of functional group that could undergo hydration, one very specific kind of double bond, and that was an alkene. The reason we did just that one is because, biologically speaking, it's the only one of any interest to us that can. If you look at other groups that contain double bonds, for instance, carbonyls or aromatic rings, neither of them are capable of undergoing this reaction. That one, no chance. There's an L in carbonyls. There we go. Now, by contrast, hydrogenation could get carbonyls involved with us here. So hydrogenation could involve C-C double bonds, just as hydration did, but we could also get it to work with CO double bonds. It is worth being careful, though. Not all carbonyls can be hydrogenated. In fact, mostly it is held to aldehydes and ketones. Hydrogenation gets a little bit trickier when you start adding electronegative atoms like N or O to the carbonyl. And so, for instance, esters, amides, and our new friends carboxylic acids, along with carboxylates, I'm going to put that underneath, none of these undergo hydrogenation reactions. Eventually, we're going to have another name for hydrogenation reactions, and so it'll be important to recognize that aldehydes and ketones are the big functional groups that are capable of doing that reaction going forward. Now, turning our attention to elimination, again, hydration, or dehydration in this case, is going to be a much more selective reaction than dehydrogenation ends up being. As far as the functional groups that can do dehydration, that is the loss of H and OH, you're pretty much stuck with alcohols. As it works out, phenols won't do this because a phenol would have to take the OH from the alcohol and an H from the aromatic ring. And if there's one thing that defines aromatic rings in terms of reactivity, it's that they don't do much of anything in biological settings. They just kind of sit there flat as pancakes and help out with structure, but they don't do much chemically. So functional groups with O's in them, alcohols, are capable of becoming alkenes. That's about it. You're not going to see this happen with phenols. You're not going to see it happen with the OHs in carboxylic acids either. As for dehydrogenation, well, there are a couple hydrocarbon groups that can do it. We've already seen that alkanes can be dehydrogenated. When that happens, they become alkenes. We've also seen that, we haven't seen rather, but we could see, that an alkene, if you were to further dehydrogenate it, would give you an alkyne. It would turn it into a triple bond in that case. The other major thing we saw that could be dehydrogenated were, again, alcohols. They are capable of losing a pair of H's. In this case, one of them off the oxygen in the alcohol and the other one off the carbon that is attached to that O. Now, it's crucial to look at that structure then if you want to think about which alcohols actually can do this. So, for example, if I have a primary alcohol where the carbon that is bound to the OH is bound to just one other carbon, it's got two H's on it, well, when I take away this hydrogen, the result is that this primary alcohol would become an aldehyde. No matter what I do, I'm going to wind up with a carbonyl of some sort, but I can be more specific. A primary alcohol is going to give me an aldehyde. On the other hand, if I made this a secondary alcohol, if I turned that H to another R group over here, well, now I would have a carbonyl with carbon on either side of it. That would actually give me a ketone. Lastly, if I make this an R group, well, now there's no H for me to take away from that carbon. And so it turns out a tertiary alcohol doesn't do anything. So keep an eye out. Most alcohols can do this, but not every one of them. You still need to actually have the H on the O and the H on the C in order to do that. Again, in the discussion of dehydrogenation, we mentioned that phenols couldn't be dehydrated. Same thing goes here, for that matter, a phenol or just an aromatic ring in general neither of those are capable of being dehydrogenated. So here's what you've got. Alcohols, alkanes, alkenes, those can all lose H's and upgrade their bonds. Alcohols can also lose H and OH and upgrade the bond between the two carbons that are losing the H and the OH. And that's about the extent of it for elimination reactions. Now, as we get ready to look at hydrolysis and condensation, let's cast our mind back to the two functional groups so far that we've seen do this: amides and esters. Remember that an amide, when it is hydrolyzed, fell apart into a carboxylic acid, because the carbonyl got an OH added to it, and an amine, because the N was cut off from the carbonyl, so it wasn't an amide anymore. An ester could basically do the same thing. The only difference was, since it had an O attached to the carbonyl, it made you an alcohol at the end instead of an amine. And both of those reactions can be reversed. So if I give you an amine and a carboxylic acid, you can make an amide by way of condensation. If I give you an alcohol and a carboxylic acid, you can make an ester by way of condensation. Now, you could be forgiven at this point for thinking that anything with a carbonyl will be able to do this reaction. However, it turns out that that electronegative atom connected to the carbonyl is really what makes that bond ripe for being cleaved. Without it, it doesn't work. So I'd encourage you, before we head back to the worksheet, to think a little bit about which carbonyl functional groups don't have a prayer of undergoing this reaction, if that's what's important. Now, there are two non-carbonyl functional groups that are capable of undergoing hydrolysis, but one of them kind of looks like it's a carbonyl-containing functional group. I'd like you to squint your eyes looking over page 138 and 139 and see if you can spot the functional group that almost looks like a double-headed ester if you just changed one of the elements. So if you've examined the other groups that contain carbonyls, you may see here that there are two functional groups that don't have a really electronegative atom like O or N bound to the carbonyl, and those would be the aldehyde and the ketone. And so aldehydes and ketones are not going to be involved in hydrolysis or condensation, for that matter. They've got their own thing going with the dehydrogenation and the hydrogenation reactions. Now, carboxylic acids, and for that matter carboxylates, look a little bit tempting because you do see, again, kind of the outlines of that ester, the carbonyl and the really electronegative atom. However, I'm going to show you really quickly why this doesn't work. If I take the carboxylic acid and I cleave the same way I did with the amide or with the ester, and I add water across this single bond as I split it, then the result is going to be this half, obviously, this half, obviously, of the original molecule, and then I'm going to use my usual logic, which is that the water, HOH, is going to add such that the OH goes onto the carbon, and the H goes onto the oxygen. And lo and behold, my products are going to be water and the same carboxylic acid I started with. So this isn't a reaction. Just write NR. Yeah, I broke some bonds. Yeah, I formed some bonds, but I got the same stuff I started with, so you'd never know the difference. So carboxylic acids aren't going to do this. Carboxylic acids, no. Aldehydes, no. Ketones, no. None of them can be hydrolyzed. The one group that has at least a superficial similarity that I hope you spotted was in fact phosphates. Notice that a phosphate has, again, this P double bound to an O, and then another oxygen attached to it that then might be attached to some carbon. Otherwise, it's got a couple of negatively charged O's attached to it as well. That is your functional group. The term that you see there is phosphate. Sometimes you'll also hear these called, and I'm mainly saying by me because I can't help myself, sometimes these are referred to as phosphoesters as well, because, especially if you ignore these parts, it sure does look like an ester with a phosphorus in it instead of a carbon. When this is hydrolyzed, it happens in exactly the same way. I chop that bond between the phosphoryl, in this case, instead of carbonyl, and the electronegative atom next to it. And again, what I end up with are the pieces. I have the phosphorus over here with its negatively charged O's, its double bound O, and then nothing. And then over here, I have the R group, whatever else is in there, the O, and then nothing. And again, I put the OH with the less electronegative atom, which is the phosphorus, and the hydrogen comes over here with that. And so what I wind up with in this case is a phosphate ion and an alcohol when I'm finished. Now, before we move on to the last group that's capable of doing this, I think it might be good to flip these all around and do a quick summary of condensation. We already knew that to make an amide, you needed an amine and a carboxylic acid, since that's what you make when you hydrolyze an amide. Similarly, it was an alcohol and a carboxylic acid needed to make an ester. And what we just saw here is that if you take, and I really should have had an N here as well, an alcohol and a phosphate, those should be able to do the opposite thing and remake the original functional group, which I termed a phosphoester, just to kind of keep it straight here, the difference between the phosphate ion and the phosphate now attached to the carbon. The third group, and the one you will not be responsible for yet, but that is going to become a good friend of ours once we get to sugar chemistry in week 9, is called an acetal. And you'll notice that an acetal, at least at the beginning, still kind of looks like a carbonyl. We'll go ahead and start it like this. If you look at this right now, this would almost remind you a little bit of an ester. The issue is, it's only a single bond here between this carbon and this oxygen, which means both of those are going to have other things attached. The carbon will usually have another hydrogen attached to it. The O is going to have another hunk of carbon. So it almost, if you squinted your eyes, it could almost look like an ester, or it could almost look like a two-headed ether. Either way, this is what's referred to as an acetal. And acetals can be hydrolyzed, and it's done very much the same way that we've observed with everything else. Again, you're going to clip this bond right here between the carbon and the O. You're going to split off the pieces. And again, because you're bringing water into this, probably should have done this up on this reaction as well, because you're bringing in water, H and OH, you're going to put the OH on the carbon, H on the O, and wind up with these. Now, your products in this case are, again, an alcohol, which means when I run it in reverse, it's going to be an alcohol and something else making the acetal. What I call this, because it only has this group right here, it's only got the one ether and then an alcohol, it would appear on the other side. This is referred to as being half of an acetal, or a hemi-acetal. And so what we'll see here is that an acetal can be hydrolyzed to give these, or these two things, an alcohol and a hemi-acetal, can provide you an acetal. All right, folks, welcome back to proper audio quality. Sorry about that. I plugged the wrong thing back into the USB after I had finished up with printing off some things. Clearly I need more USB inputs on my laptop. Anyhow, moving on with things. Before we leave off on reactions, I just want to kind of touch on this fact that those four trios of functional groups, these two things make that, or this hydrolyzes into those trios are each the thematic ones for a particular kind of biomolecule. When we talk about amines and carboxylic acids making amides, that's how we make proteins. And when we go the other direction and hydrolyze the amides, that's how we digest proteins into their component amino acids. Look even at those functional group names, amine, acid. That's what you got there. The alcohol and the carboxylic acid making the ester is how we make triglyceride fats. In fact, you'll see those triglycerides sitting there in the table of functional groups as the representative for both esters and, for that matter, alkenes. The alcohol to phosphate making a phosphoester linkage is how we string together nucleotides of DNA or RNA to make long strands with specific codes in them. And as I mentioned, the alcohol to hemiacetal making an acetal is how we condense sugars to make things like sucrose or starch, big, complex sugars that are necessary for a variety of dietary needs. In fact, constructing that hemiacetal group in the first place is going to be the last reaction that we do have to learn in this class, but that's not coming up until week 9. In our last couple videos this week, we're going to turn our attention to actually giving names to the molecules that contain these functional groups and these alkane backbones. And you'll see how each piece of what we've been seeing fits into a different spot in the name. Meet me there.